Welcome to section 9.8. This is called power series. All right, so we just got done doing quite a bit with Taylor and Maclaurin polynomials. And as I have shown you in the notes here, the higher the degree, the better and more accurate you had for your approximations. If you could get up to 8th degree, that was better than 7th degree. And the other thing too is the closer to the centering point you were, the better the approximation. The difference between Taylor and Maclaurin polynomials and using power series, which is what we're going to do today, is that power series actually make it all the way up to infinity. And so therefore, you're getting the function exactly instead of an approximation. All right, you can see that a very similar approach has been taken. If you're centered at C, you can still see the parentheses, the x minus c's. You can see them going up, by powers, first power, second power, third power, and so forth, all the way to the nth power, and n is going from 0 to infinity, so you're covering the whole world here. The a sub 0, a sub 1, a sub 2, those coefficients, we can calculate. And we're going to take a look at these, but first, these are extremely useful in real life and extremely powerful, power series are. You're going to see in the next couple sections where there have been some things in the past where we could not integrate. For instance, sine of x over x. Good luck with that. You can't use of it. Even weird stuff like integration by parts doesn't work. But the back end of chapter 9 will allow us to do this by hand using some power series. You've already seen that calculators are programmed using power series and Taylor and Maclaurin polynomials. All the trig functions, sine, cosine, tangent, all the logarithms, and even your inverse trig, your arcsine, arccos, arctan, are all programmed using this stuff. But it's not just about integrating or programming calculators. The Fourier series, which is a very practical power series, has a lot of applications. You can analyze people's fingerprints using power series. Power series are behind the scenes in the setup of MRIs. In fact, a good friend of mine lives in Youngstown, just outside of Youngstown in Austintown. And the reason he decided to live there is he fixes MRIs for a living, and he does hospitals both in Cleveland and Pittsburgh, and that kind of puts him halfway. He's like, Jeff, I use this stuff every day. I'm like, that's crazy. All your digital photographs that you guys have in your storage, all your JPEG files, all that stuff is based on power series. And again, just like more terms make a better approximation, the more terms you have, the sharper your image. Music synthesizers, this is all over the place. Spectral analysis, gravity, magnetics, elasticity, heat conductivity, this stuff is all over the board. So who knows what you're going to use it for? Maybe you're going to make something wetter than water, like my former student did that I told you about. So anyway, we'll get into this starting now. This is so easy, it's a joke, but I've got to start somewhere. It says, identify where each power series is centered at. And if you're thinking, no way. No, you're probably right. Number 1 is centered at 3. For number 2, I see the alternating component, but that's okay. It's still centered at -5. And 3 and 4 would be 4 and 0, respectively. 0 because of the lack of parentheses on the x. Okay, can't stay easy forever. At least not that easy. Hopefully this won't be too bad. Power series are only useful to human beings when they converge. You can't do all that cool spectral analysis or analyzing fingerprints, MRIs, digital photographs. None of that stuff's going to work on a diverging series. So because we care about these things converging, we want to find what's called the radius of convergence and the interval of convergence. All right, there's 3 possible scenarios for convergence of a power series. The power series is always going to converge at the center. The center is the place where everything is perfect. And the center is that point labeled C. Maybe the power series only converges there. Maybe in case 3, the power series converges all the time, all real numbers. But the most common is the middle, case number 2. The power series converges for a while, but when you get too far away from the center, bad things happen. We've already seen that with the graphs earlier with the Taylor and Maclaurin polynomials. So usually there's a center, and what we call the radius of convergence is the distance from the center to the edge here. This is also the radius of convergence. Doesn't matter which way you go. That's r. And the interval of convergence is sort of what I shaded in red. And it's on that interval of convergence that we're safe. We want the power series to converge, and so we need to stay in those red locations. Okay. Section 9.8 is going to be a 2-day affair. I will do my example problems 5, 6, and 7 today. I already did 1 through 4, but they were so short you didn't even notice them. That's where things were centered at. So 5, 6, 7 today, we'll break, and then I'll teach day 2 next. So number 5, we want to find the radius and the interval of convergence on this guy here. And it's a summation from 1 to infinity. It's x to the n over n. And you remember when we learned the 10 tests in the first half of the chapter, and I said, man, ratio test is your go-to? I wasn't even talking about this stuff yet. We use ratio test almost every single problem. That is the ultimate test. So what I do is I start out by doing what I do on the ratio test. I make the limit as n approaches infinity. Remember, we crank up the powers of the n's by 1. So instead of it looking like it does, it's x to the n plus 1 over n plus 1. And we divide that by the regular equation, just x to the n over n. And again, I normally never write this step because I know it's a bit of a waste of time. I immediately just divide by the fraction in the form of multiplying by its reciprocal. So you can see I did that over here. Just flip the second one upside down. And that's going to work out to x because, again, we're taking the limit as n approaches infinity. By L'Hospital's rule, this is going to be 1 over 1. And you can see that you have 1 extra x in the numerator. I don't know what n is. If n is 1,000,000, then you've got 1,000,000 and one of them on the top and 1,000,000 on the bottom. You're going to cancel 1,000,000 of them away. There's still 1 left. All right, so it's going to turn out to be this. Now remember that if you want the series to converge, and we do because we're looking for the interval of convergence, the radius of convergence, not divergence. So you need to set this less than 1. That's how the ratio test makes things converge. Well, if the absolute value of x is less than 1, what that means is you have to be between 1 and negative 1. All right, so if you're between 1 and negative 1, you can tell that your radius of convergence is 1. Because if you look at this interval that we have, from negative 1 to positive 1, that's a distance of 2. There's no such thing, by the way, as the diameter of convergence. I just made that up. So the radius of convergence would just be from the center point, which again, this is centered at 0, out to either edge. So from 0 to 1 or from 0 to negative 1, the distance is 1. So that's the radius of convergence. All right, now, here's the thing. This is not the interval of convergence. This is the unofficial answer. And by the way, we usually don't use these symbols, the less than signs. Usually if it's less than, we'll curl it. If it's less than or equal to, hard bracket. Kind of like we did first semester for a little while. Those are back. It's called interval notation. And obviously we're finding the interval of convergence, so it's probably wise to use interval notation. Right now, our unofficial answer is this. In interval notation, negative 1 to 1. To make it official, we need to check both endpoints for convergence. Sometimes the endpoints converge, sometimes they diverge. So we're going to try the negative 1 and the positive 1 in. We're going to do that right now. So again, this is the unofficial interval of convergence. We're going to try the endpoints. Let's try the negative 1 first. Negative 1, get in there. Let's bounce that back over to here. That's going to be negative 1 to the n over n. That's AST. That's going to converge. Since the negative 1 converges, turn it into a hard bracket instead. All right, now the positive 1 is going to make its way in. And that's going to give us this. Well, that's a diverging harmonic p-series. So that is going to diverge so we don't make it a hard bracket. That's not part of the interval of convergence. So the official answer now is this. Notice hard bracket on the negative one because it does converge. But curly parentheses on the positive one because it diverged, so it's not included. All right. So the radius of convergence was 1. The interval of convergence is right there. -1 to 1, hard bracket on the negative. Okay, this time around we don't have any pre-made step-by-steps. We're going to just go in cold. We want to start with the ratio test always. And you can see that this one is centered at x equals -1. So it's kind of interesting that we should come up with something centered at that point. So starting with the ratio test, it's the limit as n approaches infinity. Okay, I moved all the n's up by a power. Now we're going to divide by the original, so we'll multiply by its reciprocal. So 2 to the n up top of the numerator. The rest of the original will be down here in the denominator. All right, looks good. Let's go. Let's cancel. First up, the -1s are gone, as always. The 2's, there's an extra 2 in the denominator. And there's an extra x plus 1 in the numerator. So that's going to give us the absolute value of x plus 1 over 2. All right, we want the interval of convergence and the radius of convergence, so we need this to converge. So that means that the absolute value of x plus 1 over 2 must be less than 1. And if your absolute value is less than 1, that means that you yourself, x plus 1 over 2, you need to be in between 1 and -1. All right, let's work some algebra. I'm going to double everything. So the middle will become x plus 1 just by itself. That becomes a 2. That becomes a -2. Fantastic. All right, let's subtract 1 from each part. Again, these operations I'm doing will not flip the signs. Greater than and less than signs only reverse when you multiply or divide by negative numbers. I'm doing neither of those. All right, that's my unofficial interval of convergence right there between -3 and +1. But I do know what the radius of convergence is. And again, remember we said early on this is going to be centered at x equals -1. And sure enough, -1 is midway between -3 and +1. And if you go from -1 to either side, the radius of convergence will be 2. Okay, so far so good. Now I need to test the endpoints to get this unofficial answer right here and make it official, because right now that's the unofficial interval of convergence. It's going to have a -3 and a +1 in it, but it may not stay just less than. It might be equal to as well. All right, we're going to test the endpoints. Let's start with the +1. I feel positive. Let's put the +1 in right here and see what happens. Okay, when you put in the x equals 1, you end up getting a 2 to the n, both in the numerator and denominator. Those are going to just cancel right out. And so it's going to be -1 to the n, which is just going to oscillate back and forth between 1 and -1, changing signs forever. That diverges. Anything that oscillates diverges. So this is officially just a less than symbol, no equal to on it. By the way, you don't have to write interval notation. In fact, a lot of times I don't. I like to go with the less than or equal to or just less than signs. That's fine. All right, let's try the other endpoint, the -3. We'll try that in red. All right, this can be slightly rewritten. We still have -1 to the n. I'm going to rewrite this as -1 to the n times 2 to the n, which is totally okay to do in your Algebra 1 class. You should be able to recognize that as being fine. Now I can do my canceling. Negative 1 to the n times another negative 1 to the n is negative 1 to the 2n. And regardless of what you plug in, your exponent will always be even, meaning that this is going to produce this series, 1 plus 1 plus 1, just the sign won't change. Well, you're not heading towards 0. The last term, when you get all the way out to the end of time, is not going to be a 0. It's going to be a 1. So if someone says, hey, what's this add up to, and you spend your whole life adding it, some little kid, when you're on your deathbed, can add another 1 at the end and ruin your life's work. So this is diverging as well. So again, it's not less than or equal to, it's just less than. And now the official answer for interval of convergence has been found. And there it is. Of course, you're always welcome to do it in interval notation as well. That's perfectly fine, just as acceptable. All right, one more problem and we'll be done with day 1 of section 9.8, day 1 of 2. All right, and finally, last but not least, number 7. Find the radius and the interval of convergence. As always, we're going to start with the tried and true ratio test. All right, there's the setup. You can quickly tell that some canceling will happen. There's going to be an extra 2x in the numerator. As far as the factorials go, this n plus 3 will be the extra piece down here. The n plus 2, n plus 1, everything else is going to cancel with this. So that's out. So you're just left with 2x over n plus 3. But remember, n is heading towards infinity. So actually what you have is you have 2x over infinity plus 3. And I can tell you what 2x over infinity is. It's 0. All right, we want the radius of convergence and the interval of convergence. If we want the ratio test to converge, we have to make sure that this little item right here is less than 1. And where does that happen? Well, everywhere. Everywhere. We've got a case 3 situation on our hands. So since 0 is always less than 1, the radius of convergence will be infinity, and the interval of convergence is all real numbers. All right, that's it for day number 1. We'll have this all finished up in just a couple of days, 2 days. All right, see you then. Bye.